Hi everyone, let's talk about aromaticity or aromatic molecules. Now these are molecules that have unusual stability. And to begin with, let's talk about the most common aromatic molecule. That would be this guy, benzene. That's an aromatic molecule. And you know what, any molecule that has a benzene ring in it, we'll put some stuff in it. We got an alkane side chain here, chlorine, OH group here. Okay, we would still say that this molecule is aromatic, even though the whole thing's not aromatic. It's really just this part of the molecule that's aromatic, but you could say the whole molecule is aromatic. It's an aromatic molecule. Okay, what's this unusual stability that we're talking about? Well, here's an example that illustrates that point. If you take Br2 and react it with an alkene, just a simple carbon-carbon double bond, the double bond goes away. In the reaction, where there used to be a double bond, now there's two bromine atoms. That's an addition reaction. If you take Br2, mix it with the benzene ring, and you recognize this as another form of drawing the benzene ring. We can also draw it this way. The benzene here in this structure has 3 double bonds, so at face value you might be thinking, hey, this reaction should be 3 times as reactive because there's 3 pi bonds to react with. Take the same reagent, Br2, and it turns out in the absence of a catalyst there's no reaction. With the catalyst, there's some choices of catalyst right here. Br2 reacts with benzene and you get bromobenzene, but it's a substitution reaction. One of the hydrogen atoms on the ring is substituted with bromine, and all 3 double bonds survive the reaction. Unlike with alkenes, the double bond goes away. Not for benzene, not for aromatic molecules. It's important to note that no reaction occurs in the absence of catalyst. So if you have a molecule that has a benzene ring in it and an alkene, and if you treat it with, say, Br2, well, the aromatic ring doesn't react with Br2 without a catalyst, but the alkene does. So the benzene ring survives unchanged. The alkene, however, goes away, and in its place you get the addition of 2 bromine atoms. How come? Why are aromatic molecules so stable? Well, taking a look at the benzene ring, so let's draw the benzene on kind of an angle here, and I don't know, if we look at these 2 carbon atoms, I should have picked those 2. Let's pick these 2 carbon atoms over here where the pi bond is. The pi bond consists of 2 electrons filling these p orbitals, and these p orbitals are close enough to overlap. And in benzene, all 6 p orbitals can overlap, and you get more of this type of structure, where instead of thinking of these little lobes as separate, little gap here, that's really not the case. They actually touch, and these 6 lobes up here form this top donut, 6 lobes down here form the bottom donut, and all 6 electrons, right? So each pi bond consists of 2 electrons, 2 electrons, 2 electrons there. So 6 electrons, 6 pi electrons. They're free to flow about those 2 donuts. We say they're delocalized because you can't pin them down. If you had a regular alkene, that double bond forms from 2 electrons filling these p orbitals sideways overlapping, and they're localized. A reagent like Br2 can find those 2 pi electrons just by attacking these 2 carbons. The pi electrons are either above or below or somewhere about those 2 carbons. Not the case over here in benzene. Where are 2 electrons? They can be anywhere in these 2 donuts. Hard to pin down. They're delocalized. Got a couple more pictures here. Got resonance structures trying to show this delocalized behavior. Got some nice color pictures showing they're all spread about. Okay, benzene is not the only aromatic molecule. So we're going to have to see, we're going to have to be able to analyze other molecules that at a glance don't look like benzene, but in fact they can be aromatic too, just like benzene. And the characteristics of aromatic molecules are here. There's 4 characteristics. If we think about the parent molecule benzene, it has a ring. The ring is flat. Sometimes that's tricky to see, but we can say it can be flat because every carbon is sp2 hybridized. Right, there's a hydrogen here. It's making 3 sigma bonds. It's got 1 pi bond. That's sp2 hybridized, which is trigonal planar. Okay, so at least these atoms are all in the same plane. And then this atom, this carbon over here, is also sp2, so those 4 atoms are also in the plane. Okay, and so it's reasonable to suspect that all 6 atoms in the ring could be lying in the same plane. So we can say it's probably planar. Conjugated, yes. Throughout the ring, the pi electrons can flow. When we look at conjugation, what we really have to do is every atom, what we have to see is that every atom in the ring has a p orbital. Right? We have to set up the situation where the pi electrons can run about the ring, and that will only happen if every atom in the ring has a p orbital that can overlap. That's really what conjugation is. Most of the time we think about conjugation where there's an alternating double, single, double, single, double, single, double. That's a quick check, but it turns out there's some other cases where it's not simply just alternating double and single bonds that makes it conjugated. And this is a better definition. Every atom in the ring has a p orbital. Finally, fourth characteristic. The molecule has to satisfy something called the Huckel or Huckel rule. 2 little dots above that U. What that means is you take 2 times an odd number, and that's how many pi electrons can be in that ring, conjugated, flying about the ring. So the Huckel numbers are where n equals 0. 0 times 4 is 0 plus 2. N equals 1. 4 times 1 equals 4 plus 2 is 6. And then 10, and then 14, and then 18, and so on. So these are the Huckel numbers. 2 pi electrons, 6 pi electrons, 10, 14, 18 pi electrons. They work. And so if the molecule has this many number of pi electrons in that ring, and they're all flat, the ring's all flat, and these number of electrons can fly about the ring, it's conjugated, then we can predict it's aromatic. Okay, that's a pretty special case. Most molecules don't satisfy all 4 characteristics, and we just say that they're not aromatic or non-aromatic. There is, however, a special case where the first 3 characteristics are satisfied and the 4th characteristic has a different set of numbers where there are 4n pi electrons. So that would be 4, 8, 12, 16, factors of 4, multiples of 4, sorry. And in that special case where the molecules are, well, they have a ring, and that ring is flat, planar, and all the pi electrons, these wrong numbers, 4, 8, 12, 16, are conjugated, well, that special case is called aromatic. It turns out that's just the opposite of aromatic. It turns out these molecules are incredibly unstable. Nature doesn't like instability, so if the molecule can bend or twist to get out of planarity and break the second characteristic, it'll do that. It'll try to avoid being anti-aromatic and getting to this really bad unstable molecule. Okay, so anti-aromaticity is pretty rare. Okay, well, we've seen a little background. Let's give it a try. We've got some molecules. And the question is, are they aromatic? Let's start up here. This turns out to be a form of penicillin. Is it aromatic? Well, right over here is the benzene ring, so you could say yes. On the exam, I'd like you to circle that portion of the molecule and say it's aromatic, because there's the conjugated flat ring structure with 2, 4, 6 pi electrons. 4n plus 2, n equals 1. So 4 times 1 plus 2 equals 6. Yep, that's a Huckel number. 6 pi electrons. Okay, but there are other rings in here, right? To be aromatic, we need a ring. We need it to be planar. It has to be conjugated throughout. And it's got to have a Huckel number. Huckel number. Pi electrons. Okay, so let's look at this ring. What's going on here? Well, these two atoms right here don't have p orbitals. They're sp3 hybridized. Okay, this ring right here, yeah, they got sp3 hybridized carbon 2. No p orbital, can't be conjugated, doesn't work. How about this system? There's 7 atoms in a ring, not 6. Benzene has 6. Is this aromatic? Well, take a look. Is it a ring? Is there a ring in the molecule? Yeah, it's mainly a ring. Is it flat? Well, it could be. Definitely these 6 atoms are sp2 hybridized, right? They have a double bond. And 3 sigma bonds. They're sp2, trigonal planar. What about this guy, the carbocation? Well, there's 3 sigma bonds here, and then that's it. It's missing a bond. This carbon only has 3 bonds. It turns out this carbon is sp2 hybridized, so it can make 3 sigma bonds, those single bonds, using an s in 2 of the p orbitals, and then there's an empty p orbital where the carbocation is. Okay. So all the atoms in the ring are sp2 hybridized, and every atom has a p orbital. It's conjugated. Okay, so we got ring, it's flat, conjugated, does it have a Huckel number? Well, there's no pi electrons in this carbon. There are 2 over here. There's 2 more here, 2 more there. That's 6 again. 6 pi electrons. That's a Huckel number. So yes, this molecule is aromatic. How about this one? Yep, definitely a ring. Check. Is it planar? Well, let's take a look. These atoms are all sp2 hybridized. Double bond there. So flat and trigonal. What about this carbon here? Well, there's the unwritten hydrogen. There's a bond here, a bond there, and then there's an orbital that holds a lone pair of electrons. Okay, normally this would be considered sp3 hybridized. Just think of that lone pair as sitting in sp3 hybridized orbital. But aromaticity is a real nice thing. It makes the molecule very, very stable. So what nature can do is say, hey, instead of doing the normal thing of putting the lone pair in sp3 orbital, let's put it in a p orbital and re-hybridize that carbon as sp2. Take care of these 3 sigma bonds, single bonds with sp2 hybridized orbitals, and then just tuck the lone pair into a p orbital. Oh, do the same thing over here too. Great. Okay, if everybody's sp2, there's a good chance it can be flat. If everybody has a p orbital, that makes it conjugated. Let's see if it's got a Huckel number of electrons. Well, starting up here, there's 2. Another pi bond's 2. Lone pair, that's 2. Pi bond 2. Lone pair 2. 2 plus 2 plus 2 plus 2 plus 2 is 10. 10 pi electrons. Yep, that's a Huckel number. 4n plus 2, where n is 2 now. 4 times 2 plus 2 is 10. The answer is yes. It's got a Huckel number. All 4 criteria are satisfied. Alright, the last guy here. What have we got here? Oh, definitely a ring. Is it planar? Check, it's a ring. Planar. Well, everybody's sp2 hybridized. So, probably. Is it conjugated? Yeah. It's alternating. Double, single, double, single, double, single, double. Everybody's got a p orbital. So it's conjugated. Does it have a Huckel number? 2, 4, 6, 8. Oops, no. That's a multiple of 4. That's the bad situation. This looks anti-aromatic. So the answer is no, this is not aromatic. Okay, anti-aromaticity is really bad. So what nature actually does is says, hey, let's not even have this be planar. Okay, not planar. And the idea is nature says, okay, if we no longer let this be planar, does not satisfy all 4 characteristics, and now it's just simply non-aromatic. Much more stable than being anti-aromatic.